Go ahead and just.
This one, should I catch something like?
You can try it, yeah.
Like this. Okay.
That should work.
Okay, super. Okay, so I can start now. So before I start, I would like to thank Gregor for hosting me and also my assistants and Vladimir. Vladimir is assistant professor. And also to all of you that show interest to come and hear this talk. So this is one idea how to try to derive effective population size by using runs of homozygosity. This is a very old idea that came from now it's maybe almost 10 years ago, like from the project's Croatian Slovenian project at that time, bilateral. We had idea, but then it was looking like it's very, very easy, but then it turns out to be very, very difficult. So it took us quite a lot of time. We were not always concentrated fully, but still I think if we haven't solved everything, we are smarter now, at least from some aspects. So this is the title of the talk. So the effective population size, this is one of the most important parameters in conservation, but also in population genetics, but also is very important parameter in quantitative genetics. So in general, this is definition. So the effective population size of a real population X is the size of a hypothetical ideal population, right Fisherian, that will result in the same amount of genetic drift as in the real actual population considered. So we are just trying to quantify this amount of genetic drift, but this amount of genetic drift can be expressed as a change in allele frequency. Then we talk about variance, effective variance population size can be just the drift of inbreeding. Then we can talk about effective inbreeding population size, can be also the rate at which genetic variants are lost. Then we are speaking about effective eigenvalue population size, but we can also speak about change in the gametic phase or linkage disequilibrium. Then it's something that I would call effective linkage disequilibrium population size. So all those coefficients are under many circumstances quite equal and comparable, but not under all instances. Sometimes they can vary because they actually measuring different amount of drift. Everything is drift, but really specifically different rate of drift. So here I would concentrate just on those ways or methods that I used mostly in livestock population genomics, but also for the people that are dealing with wild animals. And this is like from the time of pedigree, one of the best methods was the method of Gutierrez. Then there is a method of Barbato. Actually, it's a software method. It's not Barbato. Method comes from Sweden and it's developed with more people. This is like linkage disequilibrium effective population size. Also in more the people that are dealing with wild animals, they are very much like livestock people were using quite much SNEP, but then people that are dealing with wild animals, they were to do NA estimators. This I would call that it's like effective population size that relates to the gametic disequilibrium. Why? Because it's not taking into account markers that are linked. And then very, very recently, very good software appeared, and it's made by first author Santiago and collaborator, and it's called GONE, or sometimes we are calling it GONE. And within this, you have combined also gametic disequilibrium, but also linkage disequilibrium effective population size. So those linkage disequilibrium and gametic, they also have one possibility to calculate historical effective population size, which is very much nice. And then I presented like at EAP, like in 2008, it's something that I would also try to show you today. So also to compare all those methods with this one and to get like experience. So usually when we are concerning in this lecture, although we are estimating other effective population sizes, we are mainly interested here on the inbreeding effective population size. Why? Because this is the one that it's more directly functionally correlated or associated with inbreeding depression and detrimental load in populations. So, and the basic formula would be like the delta F is 1/2 times n effective population size, or effective population size is 1/2 delta F. This would be something basic. So if we would like to estimate effective population size in the current population size, inbreeding one, we would need to know inbreeding in the current level of inbreeding in the current population, but also level of inbreeding one generation back. But then drift for the small populations, drift can be so strong that you get like quite variable results. You know, your estimates are not stable, or confidential intervals are very, very long. Or at one step, inbreeding can go also up and down. So if you see in this formula, if you get negative delta F, then you are not able to estimate effective population size, or the estimates go to infinity. Just the formula is not defined. So how we are then trying to be more precise? If population is stable and the amount of rate of inbreeding delta is just slowly and gradually rising, then we have opportunity to do our estimates based on more information, based on more data. Like, for example, in this example, you would see like by regression, we would not get really a negative value because then in the whole period, it's not likely that we would get like negative all trend in inbreeding if population is close and under all conditions. So this is the method developed by Gutierrez. So how Gutierrez, what is the basic of his method? So the basic, he started actually with from like this formula, but another formula, which he said to try to calculate delta F. So how he based this? What was the idea in his method? In his method, he would say that each individual inbreeding coefficient calculated from the pedigree is just inbreeding that has accumulated from the founding populations in the pedigree up to the, so how long is the pedigree? Then this accumulation of inbreeding is just relative to this time of accumulation, you know, like. But then how in a pedigrees are not always complete. So he just made a substitute. So in his first, he made a small error. So he put it like this. Actually, this would be like you are averaging, let's say I got inbreeding of 0.1. And then if it's 10 generations, accumulated over 10 generations, that would mean that in one generations, accumulation is just 0.01, and then we would be able to calculate effective population size very easily. In his case, he was a little bit tuning the formula because he realized that in one generation you cannot have inbreeding, that the best is you need at least 2 generations. So in computer simulation, he realized that he's missing some part, and then in the next paper, he just make like formula that it's Ti -1. And in his case, what is Ti? This was like complete generation equivalent. This is a measure for the pedigree quality. Like it's assumed this is the completeness of the pedigree that is fully complete for, let's say, 5, 6, 7, or 8 generations. There was also one very, very nice point in his. Usually, we would estimate inbreeding just as a single value. And in his method, he would be able to calculate, actually estimate effective populations for each individual, but then averaging over those individual, and it will allow him also to make confidence interval, also to get some reliability or somehow to get the more confidence on this estimate. So the next is actually, I'm putting like the name of Barbat, although I should accredit some other authors like Sved, Ben Hayes, Albert Tenessa, but this is actually like the formula under which SNEP is working. And then it has been shown in the paper of Corbin and also like participating in, I think, contributing a lot from John Williams, that like the method of this is not precise on the in the current population, and let's say up to some 10 generations. So you would get like very imprecise, very not reliable estimates. So recently what I did, like for example, I would like just do estimates and then I would count I would collect the information of some historical estimates, for example, from generation 10 and then later, and then would do just linear regression to predict what's going on in generation 0. So this is how I would do. I must admit that I had feeling that during all those that the values were a little bit lower than I would expect. But this is then maybe this correction is not good. Although I think in the Hayes paper or Albert, it was said that this method is functioning if the decay of population is like also constant, and it is expected that it's linear actually. So we would not expect big jumps. And then this is classical formula that stands behind NA estimator actually. And first I would start to introduce you a little bit to the concept of runs of homozygosity. So in the concept runs of homozygosity, we are measuring like the strings of regions that are homozygous, like in a very, very big. And so those regions are so big that we assume that it's impossible, like they are just fluctuating, randomly segregating haplotypes in a population that would come together in a homozygous way. So we assume, okay, they are so big that this is just a consequence because they are autozygous, or there is some relative very close that the chunks were haplotypes long were segregating. And it's quite obvious that if our ancestor is very, very close, so those we might expect also very, very, very long segments. And if it's more remote, then we would expect much shorter regions. Why? Because, of course, in between we expect a recombination rate. But as we expect recombination rate, this means also recombination rate is another parameter that is affecting also the estimation of runs of homozygosity. But then runs of homozygosity are having one very nice property. There are existing like theoretical expectations that would say if it's like 10 centimorgans is the runs is big, or if we would just roughly say 10 centimorgans is equal to 10 megabases, then expectation is that this segment is derived from an ancestor that is 5 generations back. This is just one example, but there are all distributions that are like making that I expect expectations, this expectation. But then also I think McQuillan is also somewhere from here, and maybe at the medical faculty. So in humans, he introduced this concept as an estimator of genomic inbreeding. And what is very nice in this region, he was saying like, okay, if runs of, I can assume, or I can define genomic inbreeding as a proportion of autozygous loci over the all loci that I'm capturing in my calculations. But then what you would really, the question is what you would really assume that they are like autozygous segments. And then it's very robust method, maybe not imprecise, but he said, okay, I can say if they are bigger than 10 megabases, I can assume they are autozygous. Or I can say also, if somebody else can say, no, I can assume if they are bigger than 5 megabases, then I assume they are like autozygous. But so in this concept, depending on how long are the segments we are assuming as autozygous, we are actually having timescale trajectory of all estimates of potential genomic inbreeding. And the nice story is, like, it's very much according to this very also imprecise, but also assumption that, like, if they are 10 megabases big, this means that they are coming from an ancestor that is 5 generations back. If they are like 5 megabases, then we can say, okay, this is, we suppose it is like coming from an ancestor that is 10 generations back. So this is a very, very, you see, imprecise method, but roughly we can get some numbers that are good. And this is also like equivalent, like if we would compare it to the pedigree method, then we can say, oh, this is just because inbreeding is a quantitative measure, inbreeding coefficient is a quantitative measure of inbreeding, but it's a relative measure. It tells us how much inbreeding accumulated since founder population. And founder population is usually in a pedigrees limited by the last founders in a pedigree. Here we can say, okay, our founders are exactly there when we have expected ancestor that our segments are coming. So in a similar way, like we have in pedigree, like generations, here we have like accumulation of genomic inbreeding since the expected animals that those segments were derived from. So you can see also that in this concept, we can also think it as an accumulation of inbreeding in a time period. So this is like, we can say, if it's like 5 megabases, then this is inbreeding accumulated in a 5 generations. If it's like that, then like here it's 5, here, sorry, this is like 10, big 10 are 5 generations, then 5 megabases are 10 generation, or 2 megabases should be like 25 generations. And if we are doing like in a very, very simple way, if we are then saying, okay, this is the realized genomic inbreeding divided by the number of generations we are looking for, then we get this actually delta F over certain period. So mainly this is classical formula, the first one, this one, that is in all books. This is actually the formula that it derives like Gutierrez. And our like suggestion is that we should do it in the same way, replace as in the pedigree, to replace complete generation equivalent with number of generations derived from the length of the segments we are assuming that they are autozygous. So if we are doing this, we can get, the idea is behind the values that are quite well corresponding to effective population size. Usually sometimes in this formula, people assume that, okay, if it's really, really starting in breeding, if it's 0, then we can only divide like accumulated inbreeding. So for number of years, my like very, very rough, when I would read the papers where people would report runs of homozygosity, I would immediately very often transform this to the effective population sizes. I was imprecise also because of this part, but on a very, very fast number, I would get quite decent numbers. For example, if I get that runs of homozygosity that are bigger than 10 megabases as 0.05, I can say accumulation over 5 generations leads me to the 001 multiplied, and very soon I come to the number of effective population size that it's coming like the 50. If I get accumulation of 005 in a runs that are 5 megabases, I can get, according to this, to the effective population size that it's like 100. And how this is working in the real populations, and the estimates we were just, if I was looking over the literature, we got quite I would say understandable or logical estimates. Why I think logical? Because small population and dairy populations would be like having smaller effective, while the meat, those that are more with meat, they would have bigger number, which is well known like in cattle, because in cattle, usually in dairy science, it's artificial insemination is more intensive, and then the sex ratio, it's also selection is more intensive, and then we have much lower effective population sizes. Okay, so the main goal of also of this talk, maybe, it's just we wanted to see how, by computer simulations, how those all effective population sizes, how they correspond to each other. And we also wanted, this was a computer simulation, and we also choose one empirical example to show how this is going in an empirical population. And in our computer simulation, we were very much interested also how these LD estimates are corresponding to inbreeding effective population size. And in the computer simulation, we were able to have really to have true autozygosity since generation. We were flagging generations 0, and then we would get really counting realized autozygosity. So this is computer simulation. So of course, Gregor is also involved. So we were choosing AlphaSimR. Gregor told me that this is an old graphic, but this is supposed to be correct. This where the program is. So in our simulation, we were thinking as a 31 chromosomes, like doing like, and the whole sequence was assumed to have 682,000 SNPs. This would be, in our case, sequence, but it would be something that we would get from a high density SNP chip, usually. While our really something that we were calling like SNPs and something that we can do estimates were like some 2,000 and something SNPs per chromosome, which at the end resulted at 65,100 SNPs per an individual. This would be more toward mimicking the situation of the classical SNP chips in cattle, 60K or 54K and so on. And we were not interested in what's going on a very long scale. We were very much interested in what is just going in our vicinity, like what is going with current estimate and some 25 generations back. So our simulations were more considered on a time scale of 25 generations, although some of you that are like working also with AlphaSim, you know that there is a pre-simulation period when the effective population size is even bigger. So in EMAC there is like also growth that is before. And we had like 3 scenarios. In one scenarios we have like constant size over 25 generations. By the sex ratio, the effective population size would be 97. Then we had scenario B. This is like sudden drop. We would have very big population up to generation 16, 207 in sex. And then we would drop it like to the first simulation, like to the 97. And in the third simulation, we would have just, so this would be like we had some catastrophe, something has happened, or some bottleneck, and then population just dropped and continued to be at the lower level. In scenario C, we had like gradual decrease in the in the effective population size. And this is like on the table. Why it's stable? Because the sex has changed like slowly and then it's like dropping. We cannot get that we like to 97, but the trends you will see. So, and this is like 20 replications. We were also doing 100, but then results, we decided to present results on 20 because the trends you can see. So in this case, you will see like GONE, PED, and then SEC. SEX were more or less right around here, while NeSEX would be like a little bit down. Then this from runs of homozygosity would be like more down, like underestimating, while NeLD-SNeP would be like quite below the values we would get. And this is like a little bit when we made like estimated runs of homozygosity genomic inbreeding, like from the generation 0 to 25. You would see that this is like real sequencing where we flagged alleles at the beginning from 0 and assuming they are autozygous. This was like perfectly going from 0 and then rising together like with the pedigree one, where we would have different estimates with runs of homozygosity inbreeding. Why? Because at the beginning we would have some setup of the markers that was also resulted from a pre-simulation. So actually this was something we did not expect at the beginning. So we would have like also starting inbreeding that would appear. So once we would say, okay, this was the inbreeding that accumulated up to this, it's not completely true because we would have some beginning where it was also in generation 25 years, for example, ago, we would also have some inbreeding that it's a result of the previous demography and so on. So this is one how they were going down. But then we thought like, okay, but what if we are considering like the delta in F from, let's say, generation 10 to 5? Is this maybe making improvement in our estimation? And according to this simulation, it seems then when we would do like this based on the segments, then we would be better actually. Okay. And this would be historical, like of those that are programs that are able to do historical. So historical SNEP was very, very down. We were very, very enthusiastic about the GONE. And you see this small, we think this is just the part of this previous, the GONE is catching even EMAC simulation when the effective population size was bigger. And this is simulations, we have sudden drop. So if you are looking at the sudden drop, you would see that even our estimates like true one on a pedigree and NeSEX that are overestimated. And you will see how come, maybe something is wrong with simulation. No, this is in fact because those coefficients were calculating under assumption that like we didn't have sudden drop. So we are actually averaging, or when estimating this delta F, we are also averaging the values when the effective population size was very, very big. And this is why they are like the values are up. So if we would go like on a pedigree on a smaller interval, then, or if we would not catch when population time, when the population was very big, then we would get much better estimates. So you would see like the GONE was also a little bit over because it was a little bit would catch and it was. And this is like historical how GONE would get it. So in this micro scenario, GONE was not able to catch this sudden drop, but maybe the drop was not too drastic, but still the GONE was like, I would say, doing very good job. Well, SNEP was really below the values that should get. And this is scenario, this gradual. In the gradual, we had a little bit GONE was a little bit up, while here NA estimator was relatively more stable. Some overestimation on NA GONE. And this is like on historical, so you would see like there is some, and then in the last generation, some very small deviation from ideal situation. Okay, and then this is like example of empirical example. At the beginning, we had empirical example that was taking Croatian Busha cattle or Podolian cattle, and then we had a problem. We could not explain everything, but then I realized that this is because those cattle have mixed animals within, and it's very difficult to so estimation of effective population size is having problem when you have mixed individuals, and also if population is subdivided into several, then it's very tricky. Everything is more complicated. So we decided, I said, okay, but if we are building the theory or looking how the behavior is, we shouldn't take like populations that are like mixed or something like that. We should stay with old Kladrub course. Why? Because it's having very nice pedigrees, and we know relatively well like the history of the real demographic history. And then we had like, and it's very nice pedigree. It's tracing up to 49 generations, but actually with this equivalent complete generation around averages 16. So it's very good pedigrees. We had two quality controls. One is like very restrictive, and one was very liberal, just to see how the number of markers also influence our empirical estimations. And then this is the result. So what result is telling us? So on a very big pedigree, we had like pedigrees like around here. Runs of homozygosity higher than 4, and GONE with smaller number of markers and higher numbers of markers was identically the same. I would say even too good, maybe sometimes I'm too good to be true, but it's like this is the estimate we had. So NA estimator was good, I would say, especially when it was like the number of markers was like more 60,000, because you would see, okay, 46 is not 51, but it's not so far, and then the confidence interval would capture this. Also, the values we would get with others. While it was less reliable NA estimator when the number of markers went to even 38,000, while SNEP were constantly doing underestimation. So, and this, we did not expect it like that this would be so in agreement with GONE. And then we did historical estimation of effective population size by GONE, and GONE was like showing that our Kladrub population had like the number was rather constant, but then it was much bigger some 11 generations back. So generation interval for Kladrub horse is around 10 to 11 generations. So if we multiply this 11 by 11 or 10 closely, we come to 100, which is the end of the First World War, when the empire was broken, and it's really documented that number of horses has dropped severely. Although in our simulation, if you remember, we were not catching the point that GONE did not catch this drastic drop. Here we see that it's catching this drastic drop. And also I have communicated with other peoples and they are all very, very enthusiastic. They have all good words for this new method that is described in the paper of Santiago and algorithms implemented in the software GONE. In some other simulation on the longer period, this is probably all those deviations that we have shown by GONE. It's because we are really looking at the micro, at the recent simulations. When they simulate it over more generations, GONE is capturing in their simulation these big drops. And also in this simulation, we were comparing it to the true inbreeding effective population size, which is having also some lag in its appearance. It's not completely reacting as linkage disequilibrium. But here is something that I would, one of important message that I would like to show. So even like in this horse pedigree, if our pedigree is going like up to here, then it would also represent the averages when the population was much, much bigger. So this is I want to show. Or sometimes some people are doing this classical like method that like they are regressing inbreeding, genomic inbreeding or pedigree inbreeding on a birth year, and then they are multiplied it by generation interval. This is people are using also something like that, and then they get different values of effective population size when they use like runs of homozygosity bigger than 5 megabases or 2 megabases. But this is logical because they are not measuring the speed. I would say like, yeah, I'm going like by the bicycle through the wall. And of course, my speed is not constant, you know. So it's, of course, my speed average depends on when I start to brake. And of course, when I was starting to measure. If I'm measuring the last 5 meters, it's not the same as if I'm measuring last 10 meters. And people should be aware of that situation. So all estimates, you should know the demography before, because then we can rely on the history to get more information to estimate the current effective population size. We also had like sheep populations like in Croatia, and this we tried like just to see, and then this is like for Istrian sheep. The median is 140, but here you have the trajectory of the GONE that it was like bigger. And this is Pug Island sheep. This is also much bigger population because this is Pug sheep is famous for its Pug cheese. This is very, very expensive hard type cheese. This was just as an example. So I would like to tell you my conclusions, and the conclusions we think we can stand. So we recommend software GONE, and it's, I think, finally we get quite reliable like method and software. So we can now start to get more benefits than before. Before we were more not so precise. So I would say this NA estimation from the runs of homozygosity, it's quite promising method, I would say, although much more work needs to be done. For example, this is like when we are averaging like higher than 5 megabases, I think we should include whole distribution of all segments, those expectations, if you've seen, like in a more complex way. In general, I think like that any estimates should be, when you are estimating, should be done with more parameters in the future. So basic is first I would do the Santiago to roughly see my demography, and then I would correct it probably with some developments in this inbreeding effective population size. So to combine something included in the GONE, which is LD and gametic disequilibrium effective populations with real inbreeding based on runs. But of course, this demography, it's very nicely like derived from Santiago. Also, one thing like it's Tom, it's having his program which is called ROH, which is a very, very nice program. And I start to advertise it more and more. I think this is more fine program. And the Tom is even, he has improved it in the last 2 months. So now his program is even more precise to estimate precisely like the classes of the historical, actually those small chunks of inbreeding, especially when you have a low number of markers. And at the end, this is like the original, like original when we started, like, and also like 2 projects that are currently financing our research. So thank you very much on your attention, and I would be happy to answer some questions.
So what we're going to do, we're going to take questions here and then be responsible for taking questions from online because we cannot hear people. So, maybe I can start with one question. Why is the SNEP tool always had kind of underestimation, if it is underestimation? That method is based on LD, right?
Yes.
So do you have any explanation why?
I don't have an explanation. So one potential reason was, did we be messed? Because in SNAP, you have to put like also number of parameters. You can include assume mutations and so on. So different setups would give different values. But if we're trying to play, but then you get different estimates, but not so big. Not so big. I think it's because the basic model is maybe not satisfying all assumptions required, actually. This is one of my assumptions. I think it's always very difficult to say something is not work. I was speaking in April, I was with Mike Bruford. He said, but we tested something, but they tested with LD. Maybe it's estimating LD very close to LD, I would say. But not, I'm not getting IBD, and other people are telling also the same. And the values we are getting with SNAP, if we would go to the cattle, they would be really, really small. Like intuitively, I would say that it's underestimated.
Okay, thank you.
Okay.
Just one question. It's about the historical NE that you're talking. There are 2 things. One is that actually in your simulated data, one of your analysis showed that one of your methods showed that the population size is increased on the older historical population. But if I understand, your simulation maintain the population size equally across the whole historical period. But however, the program is actually showing that it is increasing.
Yes.
So this is wrong, no?
Sorry, I think we should come to the slide so we know exactly what we are. You think on this one?
Yes.
This is gradual, like.
Yeah, but it's historical. It was supposed to be equal, no? That was the way it was simulated. Was the thing. I understand it.
Yeah, and you never get
it should become flat.
No. The real life is very complex, and you never get the real what you get, even like in this simulating, because also it's inbreeding effective population size. For example, in LD, you would get like estimate like if you have just only 2 generations. In LD method, you will get something. In inbreeding, you will not.
In real life, there's variation. I agree with all of that. In real life, will be variation down or up. However, that's consistently showing that if I would have gone to 500 generations, I will actually end with a population size probably which is bigger than the
a little bit.
population you have.
Yeah. You would get in this scenario like a little bit bigger, but you would still observe this fall, you know.
Very, very good.
You say that your population AlphaSimR
No, Ricardo, maybe this is better. Maybe this is better, you know. You're getting the same, but then it starts to go up. Because
yes, that's my argument. That
yes.
You say that N gone.
Yeah.
You
Yeah.
more or less advertising because it does show a curvilinear, but I was understanding that the NE was supposed to be flat.
Yes, but you have pre-simulation, you know, like which is capturing still. He started to recognize the historical was bigger before.
So,
and then we were discussing with Gregor, you cannot get rid of this pre-simulation easily, isn't it, Gregor? Like
the reason I was saying because you actually see the real data.
Yes,
you
yes.
see that in the historical population, at the end you end with population size of 12,000.
Yes, yeah.
If I would have gone further, I would have got the 1 million, and I wonder whether gone actually is the further just showing that the further away you go in historical, you simply start.
Yeah.
So it become.
No. If you would get to original papers of Santiago, they have made simulations that is more on a long term, you know, like. And then on a long term, you would see that it's quite good.
So you are happy with the number that you are getting, effective population size, 12,000, for example. Sorry, what's that? I don't know.
No.
No, in the real data. In the real data, you are getting a number. 1,000. The other one was much bigger.
You think like here?
6,000.
Yes.
You're happy with this number?
I'm happy with this number. Because I think with sheep, it was like the number was much bigger. And you come actually, so the concept of breed is not so old. It's not old even here in UK, and in Balkan, the concept is extremely young, and you would get up to the very much to the meta population of the Balkan sheep. Actually, this is, you are coming. And then when we were comparing like more our populations, at certain time they would come to the same point. Now I'm like feeling sorry that I did not show like also this trajectory when they merge together actually. And this is happening like continental populations, and then island populations, they merged in some other values.
Hi, thank you for your talk. I just started recently with population size, and I'm working with what populations. In this case, is that you working with close population, right?
Yeah, no, go with question.
And in that case, do you are related in the present in this analysis that you know are.
Yeah, I include all individuals.
Because I've been struggling with that question.
I think the answering, I think you should not be biased when sampling, but if some people are like kicking out the relatives, for example, but then you are not capturing the original structure of population. If you are sampling, I think you should just not be biased by any decision. But if you are random or fair, geographic, or I don't know, all other, and then if you capture relatives, I think they should be included, even if they might affect analysis, but then you should be aware where they affect analysis because you are capturing their structure, isn't it? Like if you are having like a population where they all are full SIPs, so you would not do analysis or what?
Oh, yeah,
Yeah.
And you can see different papers.
And
The other, but
yes, and then, you know, like the concept of inbreeding is here, like in a population based on like a pedigree, it's based on a basic populations. Like some other genomic coefficients that then they are referring to the, let's say, Hardy-Weinberg population. So they are measuring deviation from Hardy-Weinberg, not from some reference population. Actually, inbreeding is mating that it's more closer than it would be at random. But even in a very, very small population, even at random mating can create relatively high inbreeding because you are capturing the structure that is really there. So you can say like, I have like very, very small populations, isn't it like? But then I still avoid mating of the most closest relatives, you know, like, and my FIS value goes to be negative because you are still not at random, but then your animals are relative, you know, like. Do we have questions? Okay.
I have one question. So maybe I missed it, but how do on the short term, the pedigree-based and genomic-based estimates compare? Do you have any graph where you show that?
If everything is like constant, you know, like then GONE would do the good job. Pedigree with true sequence, they would almost overlap.
So GONE, you can use it with genomic and
Yes.
Okay.
So what I would like, for example, for this Kladrub core, what I would recommend people to do now, let's say now and before 2 years or 1 year, I would not do this, or I would not get it. Like I would first use the GONE, and then I would see just what GONE is, what shape demographic is suggesting, and then I would try to play to estimate inbreeding, let's say with the pedigree, but then avoiding those when the population was big. You know, I would restrict my pedigree, or I would also release my pedigree. So I would see if it's affecting, you know, like the period that was like, I see in the GONE, I see the drop, I would play, you know, like with data. I would average over the period when this was not happening, demographic. And I would just see, okay, if I'm going back, it's the same like with GONE, and this would confirm me, you know, like. Then I would get, okay, I would believe GONE even additionally that it's doing good job also, but then also I would have very good exact pedigree values, you know. I have.
Any further questions? Do you have anything online? No. Okay, then, Ino, thank you very much.
Okay, thank you.